Hello. Today we are going to learn some more properties of conditional expectation and then the new topic conditional variance. So that's why the name of the today's lecture is Conditional Expectation 2.0 and Conditional Variance. So now let me start with recalling what was conditional expectation. So the conditional expectation of a random variable x given another random variable y equal to y is sum over x time probability conditional mass functions. Now recall that it was a printing mistake in last lecture. It should be x for the case of discrete random variable, and for continuous random variable it should be minus infinity plus infinity x conditional PDF xy x dx. This for continuous case. Okay, so similarly if we have a function of x, so you can do it whatever you get a function of x and y equal to y, you can write down as summation x gx conditional probability mass function for discrete case, and minus infinity to plus infinity gx into conditional PDF probability density function for continuous case. Okay, so now let me discuss some of the properties or remark. So let me just remark. So remark 1. So what happen if let x and y be independent random variables, then what happen then? So let me do it for discrete random variables. You can do it for continuous. So then you know that this quantity equal to y, this will be x, and then okay, and then this is nothing but the joint probability mass function e xy divided by the marginal mass function, and because x and y are independent, the joint probability mass function is nothing but the product of individual marginal mass function. Okay, so this you can write down as marginal mass function of x and marginal mass function of y, and then this portion get cancels, and then you will have this summation over x, which is nothing but the, you can understand, this is nothing but unconditional, this is the unconditional expectation. So conditional expectation become unconditional if y and x are independent random variables, right? So this is remark 1. Now remark 2, what happen suppose you want to find out, so you know that this gx is function of random variable x, and you want to know what happened to this quantity, okay, given that x. So you remember last time we defined that expectation of x given y, this is some function of y, this is some function of y, right? So this is a function of x. So what is this? So you can easily find out this quantity. So to find out this function of x, so it is better to know the value, right? So you know that this value the value it's in this function takes at the point x is nothing but, by definition, the expectation of x at x equal to x, right? Now when x equal to x, then gx become g small x, okay? And then so this is what this is, it's nothing but so this is the expectation of something constant thing. This is not a function. So this is gx. So at each point x, this quantity takes value gx, and hence expectation of gx given x is nothing but the function of x is clear. So you can say that this is kind of constant term. So this comes out, okay? So okay, so now okay, so one more thing I just want to clarify. Yeah, so expectation of, okay, so gx, so I want to calculate this function at the point x, and that will be x given this, and by definition this will be gx, or rather I can say that summation. Okay, so other way you can also compute it by definition from here. If you compute, so let me check it one more time. So if you compute this thing, and then what happened to this? So this will be gx times conditional mass function. Yeah, so gx is probability mass function given x gx comma x. Okay, yeah, but I think this is okay, fine. So this value at point x, it is taking this, so yeah, so this should be this, okay. So now one more property you will discuss. So we don't need this portion, we just remove this portion. Okay, so yeah, so now go to the next property. So now so let you have two random variables, so let x and y be two random variables such that uh, we such that we have to predict the value of y in terms of the value of x. Okay, then what we can do? So what does that mean? That means we need to predict something. Say these predictions of y is something, say g of x, function of x, such that this prediction is very close to the prediction of y equal this, such that it minimizing these quantities. What is the quantity? So we have y and then gx, which is a function of x. So we can ask what about this expectation, whether it is minimum or not. So minimizing this quantity. Minimizing this. Okay. So can we predict, given the function value random variable x whose values you know, can you predict the same for y or not in terms of the values of x? Okay. So in this case you have this theorem, so that tells you that the conditional expectation is actually the best predictor. Best predictor means what? So it means that expectation of given any such function gx, so expectation of y minus g whole square is always bigger than equal to expectation of y minus expectation of y given x whole square. So this y, thus expectation of y given x, which is a function of x. So this is the best possible choice of gx. So gx is also a function of x. So this is the best possible choice of gx. So how to prove this kind of theorem? So let us prove it. So we will start with the conditional expectation. So let's start that what is expectation of this quantity y minus gx, okay, whole square given the random variable x. Okay, why? Because we know that expectation. Okay, so I will tell you. First calculate this quantity. So this quantity we can modify a little bit. You can write down as y minus expectation of y given x plus the same quantity. I'm adding and subtracting the same quantity y given x. Okay, so this is y given x minus gx whole square given x. Okay, so and then you can write down this is kind of your a and this is b, so it becomes a plus b whole square, right? So you can write down s square plus b square, so in plus 2ab. So with that formula I can write down this first term is y minus expectation of y given x whole square given x, okay, a square, and then b square. What is b square? B square is expectation of y given x minus gx then whole square given x. Okay, so and plus 2ab, so 2 times expectation of these two quantities, y minus expectation of y given x into expectation of y given x minus gx given x. Okay, now let us, so now this second term, you see the second term here, you have expectation of y given x, which is function of x, and gx function of x whole square, and given x. So this is kind of a this is kind of a working as a constant, right? So as property 2, so this portion is kind of a constant, so we don't care. So this is then our goal, interesting part, and then we need to calculate this third term. Now what is the third term? You see again inside third term, you have this term which is also function of x. Oh sorry, this is capital X, function of x. So that can think a constant, so you can take out, okay, with respect to x. So so now the third term, so third term is what? Third term you can write down as expectation of y minus expectation of y x into expectation of y given x minus gx given x. Okay, so this is can come outside. This is function of x, and you are doing expectation with respect to x, so this can come outside, and then you have expectation of y given x and then inside part is expectation of y minus x given x, right? Now expectation, the linearity property of expectation tells you that the inner part, so let me just write down the outer part. This is the outer part. Then if you use the linearity property, so you'll have expectation of y given x minus expectation of so see, so expectation of y given x is function of x with respect to x, so this will be constant, so this will be expectation of y given x. Is clear? So and hence, so this person is 0, so this person is 0, so hence you will have 0. So you can understand that the third term vanishes and the second term is also a function of x, so it is nothing but expectation of this. So only interesting part is this. Okay, so this portion is expectation of something which is always whole. So this portion tells you this is expectation of y minus x minus gx whole square, and which is always equal to 0, non-negative. Okay, so using these two formula, we can find out that expectation of the initial things which we started. Okay, so given x, so this is always greater than equal to the first term. What was the first term? First term was expectation of y minus expectation of y given x, then their whole square given x. Okay, clear? And then you take expectation both sides. So if you take expectation both sides, now taking expectation both side, we get our desired result. So what is the result? So expectation of y whole square is, so always bigger than equal to expectation of y minus expectation of y x whole square. This, okay, this is true because as you know that expectation of x equal to expectation of x given expectation of there will be an expectation of y. With this formula we learn instead. Okay, so using this formula you can find out that this quantity is always following this inequality. So what does that mean? That means expectation of y given x is the best predictor for this best possible function for gx, by which you can predict the random variable y. So expectation, conditional expectation has a interesting meaning by which one can predict. Okay, clear? So this is one way of thinking these things, and then one more thing we need to discuss, and this is called um, expectation of sum of not random variable, sum of random number of a random variable, sum of a random number of random variables. Okay, this is very interesting. So we already know that if we have random variables and if you have a sum, then how to do expectation. This is linearity. Now we just want to know that similar kind of property should be true for sum of a random number of random variables. So let me give an example. Let me give a best possible example on this situation. So you know that due to this coronavirus spread, the COVID-19 threat, so our honorable Prime Minister announced a fund called PM Prime Minister Care Fund. Minister Cares Fund, and it's expected that people should donate on this fund. Okay, so now suppose that there are like n number of people, so let n number of people are donating in these PM Cares funds. Okay, and then this n is actually random variables, so you don't know that what is the exact number of people. It can be less or more. Okay, So n is a random variable which counts the number of people who are donating. So let me assume that we are kind of homogeneous population. So for example, the central government employee, like we need to donate some portion of our salary, and we are donating that. So suppose that this one particular homogeneous portion of the population, they need to donate. They are donating in PM care funds, and then what is the number in count? How many such people are donating? Okay, and then and suppose the donation is a DI, so DI. Uh, there are the donations. Okay, donations, and say which has something, say some common which has some common expected values. So for example, this central government employee, they need to donate some amount which has some common expected values. Okay, say donation as. So if this is the condition, then we need to know what is the total expected. Um, then question is that, okay, so what is the expected amount of money um, money uh, in that fund. So money uh, expected number of money, amount of money in that fund. Okay, so so you understand that you have DIs like D1, D2, D3, they are the donation, and they D1, D2, D3 are the random variables, but they have a common expected values. So expectation of DIs are equal. So what are the assumption? Assumption are the expectation of DIs are something same, which is equal to expectation of. So let me write down something expectation of D, and another assumption I'm assuming that these DIs and ends are independent. So DIs all are independent each other, and N also independent. So under this condition, my question is that what is the expected sum of the money that can raise in that Prime Minister Care Fund. So now let me try to understand this problem. So we can have this the question is kind of finding this new random variable y. So y is kind of summation di and I equal to 1 to capital N. So capital N is the random variable. So if capital N is a number, then this will gives you some of random variables which already you know how to find the expected values. But when capital is random variables, then this will give you sum of random numbers of random variables, which is the caption of this person, expected sum of random number of random variables. Okay, clear? So Okay, so 1 minute there is a problem, so let me find out what is happening here. So this process, then this, this comes, this. So this should be no, this comes. Okay, so yeah, so after this, and then this, and this. Okay, so this is, so then what we need to find out? So we need to find out this quantity, expectation of y, which is nothing but expectation of sum over di I equal to 1 to capital N, and capital N is also an random variable. Okay, clear? So now we need to find out this, and we know that this quantity is nothing but expectation of uh, expectation of sum over I equal to 1 to n di given capital N. Okay, this is the property we already proved in my last lectures. Okay, so now try to find out what is this quantity. Okay, so this inner expectation, so let us try to find out the inner expectation. So to find out the inner expectation, we start with this. So expectation of sum over di I equal to 1 to n, given n equal to the value at n equal to small n, say n small n number of people are donating in the PM CARES funds, and then this quantity is nothing but when capital N equal to small n, then the sum become I equal to 1 to small n di, okay, and then n equal to small n. Okay, now because di's and n's are independent, so this is nothing but expectation of summation over I equal to 1 to small n di's. Okay, so this is because of di's n are independent, that we already proved in the first half of today's lectures. Okay, so and then using the linearity property, it is nothing but sum over I equal to 1 to n expectation of di, which I assume that they are almost they are, the expected value is the same, so it's something expectation of d. So I can write down it as what are the expected values. So this is n times expectation of that values d. Okay, everything is d. So for each point n equal to n, it takes value n times n. So what does that mean? That means the function, this is as a function, expectation of di I equal to 1 to n. This is a function of n, which is nothing but n times expectation of d. Okay, expectation of d is something expected value of some common random variables. Okay, and so this is the function, so function of n. Clear? And hence using the formula that expectation of y, what we tried to find out was expectation of sum over di I equal to 1 to capital N, which is nothing but expectation of n times expectation of d. Okay, and hence expectation of d is a constant, so that comes out, so expectation of n times expectation of d. Okay, so this is the answer. So what does that mean? So that means that if the expected amount of donation is a expected amount. So somebody is giving 25 crore rupees, somebody is giving say 10,000 rupees. Okay, so suppose the average value is 10,000 and the expected number of people who are um, donating, it's say 0.1% of the population. So our population is what? Say 1.35 billion. So 10% means 135 crore. 10%, 1% mean 1.35 crores, right? So 0.1% mean almost 13 lakhs people. So let me write down that 0.1% of the population are donating the money, the expected values. So then the amount will be something 13 lakhs. So roughly so 1 2 3 4 5 6 7 13 lakhs into something say 10,000. So this amount will be 13 into 1 2 3 4 5 1 2 3 4, so 10 to the power 9. Okay, 13 10 to the power 9, and you know that 10 to the 9 means billion, so this is 13 billion. Yeah, so this is roughly 13 billion rupees will be gathered in the Prime Minister Care Fund. Okay, so this is an example how to find out the expectation of sum of random numbers, some random variables. Okay, clear? So by this we will stop for the expectation things. Now we will learn this new topic, conditional variance. Conditional. Okay. So you remember we defined that the variance. So if x is a random variable, then we define the variance of x by expectation of. You remember that? Probably you remember x minus expectation of x. Okay, and then whole square. Clear? Now if you have another random variable y, then we define this conditional variance by this. Okay, so this is nothing but the expected values of conditional expected values of x minus expectation of x given y whole square. Okay, clear? So this is the definition. And similarly, as for unconditional variance, you can also calculate, you can simplify this thing, and if you simplify this thing, then this will be nothing but x square minus x expectation of x given y and 2 times plus whole square x given y. Okay, and the whole thing given y. Okay, and now linearity property tells you what this first property will, first portion will be expectation of x square given y, and then the second term you will have expression of x given y is constant that comes out, so you will have expectation of 2 times expression of x given x, and then minus 2 times, and then you have plus 2 times, so this is minus expectation of x given y whole square. Clear? So now you remember the formula for unconditional variance was same, expression of x square minus expression of x whole square. So here you have only that uh, given condition. Clear? So, but we have a very interesting formula that involves both conditional variance and the conditional expectations. So let me write down as a theorem. So the variance of a random variable given whatever random variable x you choose, and if you have another random variable y, then satisfy this lesson. This is variance of expectation of x given y plus expectation of conditional variance. Okay, so this is the interesting results. Okay, now how to prove this kind of results? So so let me prove it. So proof. So now you recall that conditional variance you can write down by this quantity. Okay, so this is we just wrote. So let me write down V for variance. It is or no, let me write down full thing. Otherwise, student will start doing this kind of cheating. So this is nothing but expectation of x square minus expectation of x y whole square, right? This is from definition. Now if you take expectation both sides, so if you take both sides expectation, then you'll have expectation of variance of x given y, and then this side you'll have expectation of x square given y. Clear? And last term will be what? Last term will be expectation of. So this means the whole square. So you'll have expectation of x whole square and then expectation. Okay, clear? So and obviously we can find out what is this term. This is by definition expectation of x square, right? Which is nothing but sorry. So this portion you can write down as expectation of x given y whole square. This clear? So this is one way. So if you take first variance and then test expectation. Okay, so if you write down this number as number 1, equation 1, then you can do the equation 2 first. Now in this case you first take the expectation and then the variance. So you write down the variance. What is the variance of expectation of x given y? Okay, now by definition this is nothing but so this you are thinking this is your random variable, this is function of y, so it's a new random variable. So by definition this is expectation of this whole square, right? So expectation of x given y whole square. Okay, and then so this is this whole square and then expectation of okay, and then this whole square. Clear? But this is nothing by expectation of x. So we will have expectation of x given y whole square minus expectation of x, right, whole square. Clear? So now you recall that this is a equation 2. So what was in equation 1? So in equation 1 you will have this quantity, here also you will have this quantity. Now if you replace this to quantity, then what happens if you replace it? Then you'll have now from 1 and 2, from 1 and 2 you what you have. So on the one hand you have variance of expectation of x given y plus expectation of x whole square. On the other hand, from equation 1 you'll have expectation, so this is nothing but expectation of x square minus this quantity. So expectation of x square minus the quantity is expectation of variance of x given y. So expectation of variance of x given y, right? Now you know that if you take this thing out this side, so this thing this side, then क्या होगा, expectation of x square minus x whole square is nothing but variance of x. So this portion will becomes variance of x, and you take this portion to that side, they will have nothing but variance of expectation of x given y plus expectation of variance of x given y. Okay, so this is the proof of our result. Now we would like to give an example. So let us discuss with one example. So for example, suppose that in some railway station, the train can come at any time, say in between 0 to t, capital T, train can come anytime, and there are at any given time small t, the number of people are coming. So number of people that arrive at a given time t. So this number of people is following, say, is a Poisson random variable, Poisson distribution. Okay, so random variables, and with the mean or expected values is, say, lambda t. So what does that mean? When t equal to 1, the number of people is following Poisson distribution with with mean lambda. When mean equal to 2, then 2 lambda, like that. Okay, so at every time people are arriving the rail station, that is itself is a random case. Okay, so it's varying over time. Okay, now we are interested to know that if the train is coming in between small 0 to capital T time, and then what is the expected number of people who are so let me write down then what is that question. What is the expected number and variance both? So I'm interested to know variance also, variance of the number of the population, number of the people. Okay, number of people that enter the train. Clear? So strain can come at any time from 0 to capital T time length, and each time in between small to time length people are coming and they are following a Poisson distribution with mean lambda t. So uh, so so at time t it can be any people, and that following coming from the Poisson distribution. Okay. So then so how to find out this solution? So what you need to know? So let nt be the number of people uh, by time t. Okay. So what does that mean? That means nt is actually following Poisson distribution with mean lambda t, and one more random variable you are talking about, that is y. So let y denote the time at which the train comes, okay, at the station. So that means what we have to find, we have to find what is n of y. That means at that time when y is varying from 0 to capital T, okay, uniformly. So yeah, so I should say that uniformly. So here this is uniform. So train can come anytime in between 0 to capital T uniformly. And whatever the time, at that time what is the number of population is there, and then they will catch the train. Okay, so we are interested to know this quantity. Okay, so what does that mean? That means, so we in particular we want to know what is expectation of ny and what is variance of ny. So this quantity we are interested to know. Expected number of people, expected number of the variance of people, right? Now let me start with one. So what is this portion? So you can write down this as, I mean, if you remember that, then that this you can write down as expectation of ny, okay, and then given that y, whatever the time train is coming, okay. So you have this expectation, and then you want to find out the whole expectation, right? Now to find out this inner expectation, if you want to find out the inner expectation, then what you need to do, you need to find out yeah, so there are two ways. If one find out the particular value, I can take the sum. So either you can find out first this thing and then do the whole expectation, or you can do the, okay, so let me first do this is inner expectation first. expectation of y given y equal to say t, okay. So what does that mean? That means this is nothing but expectation of nt. When y equal to t, then it become nt, okay, given y equal to t. And what does that mean? That means this is nothing but expectation of nt. Y is taking value t, and we know that nt is an y and n. This is because this y and nt are independent. Okay, so now we know that what is nt. So nt is the most random variables whose expected values is already given lambda t. Okay, so at each time t, this expected value is nothing but lambda t. So what does that mean? That means when y equal to t is taking value t, but this is a function of y, right? This is a function of y. So that means the expected one of n of y given y is nothing but lambda of y. Okay, because at y equal to t is taking value lambda of t. Clear? And hence uh, uh, from this formula, okay, so you understand these things. So if to find out this, you need to find the expectation of this. So expectation of n of y is nothing but expectation uh, expectation of lambda y. Okay, now lambda is constant, so then expectation of y. But y is what? So y is a uniform random distribution, random variables. Y is the time of the arrival of the train. Okay, so it uniform distributed from 0 to capital D, and so expected values is nothing but t by 2. So this is t by 2. Clear? So we get that the expected number of the people who arrived at that time when train arrived and they enter into train is nothing but this quantity. That depends on the time t. Clear? Okay. Now what is the variance? So now let me calculate the variance part. So uh, so conditional variance formula. So you remember conditional variance formula. So you start with the conditional variance. So variance of n y given that y equal to t. Okay, so this is nothing but variance of n of t given y equal to t. Again, y and n t is independent, so this is nothing but variance of nt. Right now, again, nt is a Poisson distribution whose mean is lambda t, and we already know that if mean is lambda t, then variance is also lambda t, right? This is already learned in the class long back ago. Variance is also lambda t. Okay, so the variance of ny given y, this is function of y is nothing but lambda of y. At each point t equal to y equal to t, taking value t, so the function is this. Clear? So this is one formula. Now if we so, and obviously we have the other one is expectation of ny over y, which is nothing but lambda y. Okay, now we use the conditional variance formula, the theorem. So what is the theorem? So let me show you. No, yeah, so this theorem. So variance, we have to find out the variance. So this variance is nothing but variance of expectation and the expectation of variance, right? Now we already know variance of conditional variance, conditional expectation. So now we need to just do it. So the variance of the from the conditional variance formula, this quantity will be nothing but expectation of the conditional variance in y plus variance on the conditional expectation. both this quantity is lambda of y, right? So we can write down the expectation of lambda y plus variance of lambda y, right? Clear? So this is nothing but lambda times expectation of y. Now remember, y is uniform distribution. Okay, so y is uniform. Okay, so let me write them properly here. So y is uniformly distributed in 0 to capital T. Okay, so and then this one is what? The variance format is lambda square into variance of y. Clear? Now expectation of y, you just recall from our previous classes, is t is t by 2. This is lambda time t by 2. Clear? And then this portion is t square by 12. This is we know already. Okay, so so the answer is lambda t by 2 plus lambda square t square by 12. Okay, so this is the variance of the expected number of people who are catching the train. Clear? Okay, so maybe you can stop here, but maybe just one more idea we just want to discuss, and then we'll stop here. And the idea is similar, so similar to expectation of random numbers of random variables, we can ask variance of sum of. So what is variance of a sum of a random number of random variables? And we have already discussed this thing for expectation, and here already we are assuming that, say, this x1 x2 whatever these sums, these are all IITs, so that means they have a common mean. Okay, and they are identically distributed. Okay, and we want to compute what is variance of sum over xi I equal to 1 to n. Clear? N is the another random variables which is also independent to xi. So n also independent to in the of xi. Okay. So under this condition, in this is homework. You can easily prove that. So let me write down the final answer. So this is variance of these sums I equal to 1 to n xi, and this will be equal to expectation of n times variance of x plus expectation of x whole square, I mean the whole square, into variance of n. Okay, sorry, variance of n, variance of n. Okay, and this formula you can easily compute. So what you need to find out, you need to find out first conditional, you need to find out for what is conditional variance of this xi given n and conditional expectation of this given n, and then you use the conditional expectation formula, and then you are done. Okay, so problem is simple. Okay, So with that, so let me stop to these lectures. I hope you enjoy this lecture, and please write down your question in the comment section if you have some. Thank you.